ताकि बाद में and let me start where we left. Let me share the screen. This is the whiteboard. तो हम कर रहे थे Banach-Steinos theorem. वो बड़ा easy corollary है once we know the uniform boundedness principle. तो okay, तो इसको ऊपर ले आता हूँ, इसको view, admit. Okay, तो हम क्या कर रहे थे? तो I've got X is a Banach space, right? And F Tn जो है Tn था. Tn is a collection, a sequence of bounded linear operators from x to y. So मेरे पास x जो है वो Banach space है, y जो है वो एक normed linear space है, and I've got a sequence of bounded linear operators from x to y and runs to 1, 2, so on and so forth, such that ये जो हर एक x के लिए ये Tnx जो है it converges to some value जिसको हम कहेंगे t of x. तो इसके अगर हम पॉइंट वाइज लिमिट लें एज अ फंक्शन, यानी अगर मैं लूं t of x टू बी लिमिट n अप्रोचेस इन्फिनिटी t n of x, सो इस तरह से अगर मैं tx को डिफाइन करूंगा देन tx इज आल्सो अ बाउंडेड लीनियर ऑपरेटर. तो t इज लीनियर मैंने कहा बड़ा ही आसान है. तो दूसरा ये भी है, हमने ये देखा कि by uniform boundedness principle, because this is a convergent sequence for each x, so therefore this is a bounded sequence. So therefore मैंने कहा था Tn का जो norm है वो होगा less than equal to some k for all n, some fixed number by uniform boundedness principle. Now if I take norm of t of x, it is already a linear operator. That's easy to prove. जैसे कि मैंने कहा. Now this is nothing but norm of limit n approaches infinity t sub n of x, right? Now we know that ये जो norm है it's a continuous function, so I can take the limit outside. So limit n approaches infinity, norm of tn of x. Now I also know that since for each n this is a bounded linear operator, so this would be less than equal to limit n approaches infinity, norm of tn into norm of x. Now look at this norm of tn. n kuch bhi ho, this is less than equal to k. So n infinity bhi ho, tab bhi less than equal to k. So it is less than equal to k times norm of x for all x belonging to x. But I am getting that t of x is less than equal to k, some positive number k times norm of x, which implies that t is continuous, and t is a bounded linear operator. And that proves our Banach-Steinos theorem. इसके बाद हम एक definition लेंगे, फिर उसके साथ एक result prove करेंगे, what we call weakly bounded. तो you know what is a weakly convergent sequence? तो हमने कहा था a sequence is weakly convergent. तो we say, of course मेरे पास x जो है is a normed linear space and xn अगर sequence है inside x. मैं याद दिलाना चाहूंगा, हमने कहा था xn converges, यहाँ हम लिखते थे weakly, to x if f of xn converges to f of x for all f belonging to x star. अगर ये true है तो हम कहते हैं xn converges to x weakly. So फिर हमने ये दिखाया था, हाँ इसको फिर हमने ऐसे भी लिखा था x star at xn converges to x star at x for all x star to x belonging to x star, क्योंकि हमने x star के सारे एलिमेंट्स को ये स्मॉल x star से डिनोट किया था इससे पहले. तो ये तो हुआ weakly convergent. So there is similarly we can define weakly bounded. So यहाँ पे हमने ये भी देखा था कि norm convergence implies weak convergence, but weak convergence need not imply norm convergence. तो हमने यहाँ पे वो सेटल किया था, वो प्रूव किया था. तो now we define something called, we write it as a definition, वो ये कि let अगर मेरे पास x be a normed linear space for a subset A of X, is normal linear space का subset X, we say A is weakly bounded. ये जो subset है ये weakly bounded है if जो इसका अगर मैं f इस पे अप्लाई करूं फिर देखूं स्केलर फील्ड में यानी f of A is bounded for all f belonging to x star. अगर ये ट्रू है तो fa को हम कहते हैं weakly bounded. Now इसमें एक थ्योरम हम करेंगे कि a non-empty subset, it is a similar notion जैसे weakly convergence है for a sequence. Now this is for weakly bounded है for a subset. लेकिन यहाँ पे एक चीज different है क्योंकि हमने कहा था कि अगर convergent है तो weakly convergent है but weakly convergent does not imply convergent. लेकिन जो हम लिखने वाले जो हम theorem जो हम कर रहे हैं वो है कि a non-empty subset A of a normal linear space X is bounded if and only if it is weakly bounded, or if and only if FA, now F is a mapping, I just have to remind you that's bounded linear, it is a mapping from X to its field. F of A is a bounded set of a bounded set for all F belonging to X star. And इस तरह से हम कह रहे हैं a set is bounded if and only if it is weakly bounded. So that's not true for weak convergence. So let me prove this theorem. It's very easy to prove. Now since f of x, because it's a bounded linear operator, is less than equal to norm of f into norm of x for all f belonging to x star, it implies that, what does it imply? If A is a bounded set in X, then f of A, यानी अगर मैं A के कोई एलिमेंट्स लूं जो यहां से बाउंडेड है तो fx भी लेस देन इक्वल टू सम नंबर टाइम्स जो कि एक फिक्स्ड नंबर है नॉर्म ऑफ f इनटू दिस सेट f of A is bounded.
बाबा ये सेल है
जाओ तुम. Then f of A is bounded. By that I mean अगर A bounded है it means that norm of A is less than equal to, यानी I should write, मेरे कहने का मतलब है A is bounded का मतलब क्या है? A is bounded का मतलब ये है कि norm of x is less than equal to sum k for all x belonging to A. Then but उसका मतलब है कि f of x जो है वो less than equal to k into norm of f है for all x belonging to A. अब ये कोई नंबर है फिक्स्ड which means that f of A जो है is bounded. F is bounded. So okay, now converse में हमें थोड़ा काम करना पड़ेगा. Conversely, suppose that it is weakly bounded. यानी conversely suppose that f of A is bounded for all f belonging to x star. So we write, इसको हम कोई इंडेक्स सेट से डिनोट करेंगे A as, let me write it xi. तो आई का मतलब नहीं ये कोई सीक्वेंस है या ये कोई काउंटेबल सेट है, हमने इसको इंडेक्स किया, हमने इसको नंबरिंग की, लेकिन बाय एन अनकाउंटेबल, पॉसिबली एन अनकाउंटेबल सेट, काउंटेबल भी हो सकता है लेकिन अनकाउंटेबल हो सकता है। तो अगर मेरा एफ ऑफ ए बाउंडेड है, सो एक्स आई इज अ बाउंडेड सेट, यानी हमें मतलब मुझे दिखाना है ये सेट बाउंडेड है, एफ अगर मुझे मतलब इफ एंड ओनली दिखाना है ना, मुझे वीकली बाउंडेड मैंने मान लिया, एंड आई हैव टू शो दैट दिस ए इज आल्सो अ बाउंडेड सेट. Now for that we use that canonical mapping. I know that every x belonging to x can be identified with some f sub x belonging to x double star. तो हम use करेंगे भाई. So what I do now we know that f of xi, क्योंकि a अब ये सेट है, अगर ये सेट में लूं, is bounded for all f belonging to x star. Now we also know for each xi belonging to x, there exists an f sub xi belonging to x double star. I should write here A. Okay. Of course, A is contained in x, such that f sub xi at f is equal to f at xi. ये definition है canonical map की, and norm of f sub xi is equal to norm of xi because it's an isometry canonical mapping. So this is true. Now therefore f sub xi at f is a bounded set. अगर मैं xi को रन करता हूं और f को फिक्स करता हूं, this is a bounded set for all f belonging to x star. So now I apply uniform boundless principle. अगर for if f the collection of functionals, लेकिन मैं apply करूंगा वो x double star पे, क्योंकि वो complete है. Now this is a collection, ये जो mappings हैं, it's a collection of f sub I, xi इसमें है, so they are a collection of mappings from x star to k. और ये जो dual है ये हमेशा complete होता है. So by अगर ये bounded set है for each f, it implies that by uniform boundedness principle, it implies that fxi in norm is a bounded set. But norm of f sub xi is the same as norm of xi, which means that a equal to, I should write this as norm of xi is a bounded set,
Baba.
which is the same thing as saying that a is bounded. तो यहाँ पर हमने फिर से एक और एप्लीकेशन देखी यूनिफॉर्म बाउंडनेस प्रिंसिपल की, to show that if a set is weakly bounded, then it must be bounded. और वन वे तो बिल्कुल इजी है, अगर बाउंडेड है तो वीकली बाउंडेड तो होगा ही, जिस तरह से कन्वर्जेंस में वन होता था. Now we want to take another important part of your of this unit second, which would be basically the last part. वो है what we call the conjugate of an operator. Now conjugate of an operator होता है, so let me see. Okay, conjugate के लिए let me define a map like this. So let X be a normal linear space. अगर ये नॉर्मल लीनियर स्पेस है तो पहले ये लीनियर स्पेस है, ये एक वेक्टर स्पेस है. So let L be the linear space. Let it be over the field K. Let L be the linear space of all scalar valued linear maps on X. By that I mean L is basically जिसको हम कहते हैं home X K. And all linear maps, all linear transformations from X to K. I'm thinking of X just a linear space, this as a linear space. So I take all the collection of linear spaces, linear mappings from X to K, usko maine L se denote kiya, right? So you have to remember now what is X star? X star is basically all bounded linear maps from X to K. So X star is basically BXK. और ये linear भी है, bounded भी है, तो you can, one thing you can clearly see that X star must be actually a subspace of L. Then clearly, because ये bounded भी है, linear भी है, और ये सारे linear maps, तो ये bounded linear maps भी इसका एक subspace होंगे, क्योंकि ये खुद एक vector space है. Clearly, X star is a subspace of L. ठीक है? Now let, अगर मैं लूं T be a linear map of X into itself. मैं क्या कह रहा हूं? मैं कह रहा हूं मैं लूंगा T which is a linear map of this normal linear space. It's just linear. ठीक है? Okay. We use T. मुझे लगता है हम ये कल करेंगे, ठीक है? Let me end it here.
Yes, sir.
Okay, मैं इसको बंद करूंगा अभी, तुम इसका देख लेना.